Okay, hello everyone, and welcome to my video explanation for homework 2. And this time I want to start with a live demonstration to make things a lot easier to understand. So basically, for this homework, we're tasked to decode a a hex dump of 15 instructions and basically show how we did it, what the code entails, and where the issue lies within the code. So let's first start with how we were able to actually decode these uh, hexes in the first place. So there are a few steps that we take, and um, here I have three hexes from the dump that I took for to show these examples myself. So the first thing we're going to do with the hexes is we're going to convert those hexadecimals to binary. Um, the reason we do this is because we read machine code in binary, and after converting these hexes to binary, we're able to identify what um, what is the instruction behind the binary itself. So here, let's take a look at some of the machine types of machine codes that we have. We have the data processing machine code, the machine code for we have the layout for the memory instructions and the branch instructions. So my approach is first thing I like to do is separate out the last 4 bits, which is the condition field. So 1110, this this is the type of binary that we see often. 1110 condition code means basically it's unconditional, right? So it iterates every time. And next 2 bits are also always easily separable. These 2 bits are mostly uh, what what identifies our op and which shows what kind of operation we're using. So the 00 opcode is the opcode for data processing. So let's write this down as we go. So we got the AL, no unconditional, and we know that this is data processing, DP. So for data processing, there are a few registers that we use. So in this case, let's see, we have the first we have the command, we have the I identifier command and the S flag updater, and then we have the first source register, the destination register, and the source 2, which we're going to get into as we keep going here. So let's first decode this part. So so the next 6 bits are related to our command. Um, so the first one, as this data processing code instruction. So the first one is the identifier of whether there's an immediate source operand in this code or not. So it's a 1, so that means I equals 1, and which basically means there's an immediate source operand. Um, and the next 4 bits is the command bit. 1101 is also used quite often, so this is basically the move instruction. So we know it's a move instruction. And this 0 here is related to the S to the S suffix, and it basically signifies whether we update the flags or not. In this case, we don't. Uh, and the next one is the source operand 0000, and the destination operand which is 0001. So in um in move instructions, we don't actually use the RN source register, so it's always 0. So the RN is actually null, and the destination register is 1, so that means basically register at address 0001, which is basically R1. So we now have this destination register. We know that we don't use the source operand, the first source register, I mean, and the second source operand is an immediate. So and this is an immediate of 0 with a rotate of 0. So what does this mean? This means we don't rotate we don't do a rotate shift for this immediate, and the immediate is um, the integer value 0. Okay, so if the integer value is 0, so we know it's a move function, and we know the destination register is R1, and we know the immediate that we move into R1 is 0. Let's see if it's correct. So it's this one, and we can see that it is correct. We'll check all of these later as we in the CPU later as well. And let's continue. I can already see from here that this is a branch function, but let's check either way. Let's first convert this to binary, of course, and then we paste it here. Okay, let's start with the conditional. Okay, so 10, 11 conditional, that means I believe it's a less than. Let me check just in case if I'm wrong. Yes, it is a less than. So let's see here. So this is a new condition, a less than condition. Let's see the opcode. 1010 is absolutely the branch opcode, so we know it's branching. We know it's a branching instruction, and then in the branching instruction, this code is a hard-coded 1, and this is the L bit. What is the L bit? L bit is basically an identifier of whether the link register is used in branching or not. In our case, it isn't, so it's a normal branch. Okay, let me just capitalize this. Okay, and then the rest is, I think, the immediate field. Yes, the 24 immediate field. So all 24 bits here is correlating to an immediate, assigned immediate. So we can decode this as well, actually. We should probably, well, the way I did it is I basically just complemented this and then added 1. So this was basically something like value of 1 plus 4, which is 5. So this is going to be the value immediate of minus 5. Let's see if it's correct. Yes, okay. So we got a value of minus 5 for the immediate. Okay, so we know the immediate in 24 is minus 5. So what happens next is, in order to get the BTA, the branch target address, we shift left by 2, which basically means just multiplying it by 4. So minus 4, it's going to be minus 5 multiplied by 4, which is going to be negative 20. So this is going to move backwards by 20 bytes, so 5 steps back. Okay, so let's see if it's correct. Alright, we got the immediate negative 20, and what is going to happen is basically we're going to branch less than, and where are we going to branch? We're going to branch, as you can see here, PC plus 8. We have to take into consideration that the PC is 8 bytes ahead. PC is 8 bytes ahead of where the instruction is. So plus 8 minus 20. So this is going to be BLT PC minus 12. Okay. So this is going to move actually. So this is actually going to move uh, 3 steps back. 3 steps back. Okay. All right. So that's for branching, and let's do. This should be a memory instruction. Let's do one for this as well. See how it works. Okay, we got the binary here. All right. Let's see. Condition first. Okay. All right. So we got the 1110. It's unconditional. AL. And then we should have the opcode. Yes. We have the opcode division. We have the opcode bits of 0, 1. So this is for memory instructions. Then we still divide 6 bits here as well, but they serve a different purpose. They all are kind of they're all used as identifiers of some sort. So first one, as you can see here, we have I dash. I dash basically means I in the previous data processing instructions, but the opposite. So if I equals 0, that means an immediate. Yeah, it's kind of weird, but that's how it works. And the second one after that is the P. It works together with the W a bit here, 2 bits later. So we combine the PW bits in order to make a combination. So 1, 1. We got here 1 and 1. So for example, PW combination here means pre-indexing. So this memory instruction is going to do pre-indexing. And what we have left over, we have the U. For the U means whether we subtract or add from the source operand. So here U is 0. So if U is 0, that means if U is 0, that means we subtract. So that means we're going to subtract from the source operand. And we got what we got left. We got the I, P, W, U, and we got the B and L bits. The B bits means whether it is a store or a load byte instead of register, which it's not. It's 0. And the L bit is basically means is it a load instruction or not, which it is not. Okay, so here what we have left, we have of course the registers. The RN register is placed the same as in the data processing, the destination register as well. And here we have 1101, so Rn is equal to 1101, which is 8 plus 4, 12, 13, R13. And we have the destination register 8 plus 4 plus 2, which is the R14. Let's see, let's check here. Yes, R13 and R14. And we got the immediate here. We got the immediate of 4. So here we have the store register function, store register instruction, and for the destination register we have R14, which is actually the link register, and R13 is our source operand. So this is going to be the stack pointer actually. Okay, and it's a pre-indexing. So pre-indexing and pushing 4, and we have the immediate 4 here. So basically this is a pre-indexing of stack pointer and goes up by 4, which means this basically pushes the link register to the stack pointer. And this is going to be very important as to why our function is crashing as we decode this further. So I've showed you all possible ways, all possible methods and formats in which decoding can happen. Decode machine code decoding can happen. So now, how about we get into the code and see how it works? And okay, so here are my instructions, all of them. This is also present in the README. So I've decoded all 15 of the hexadecimal instructions here. And how about we do a sanity check? Let's see. Let's copy the code from the homework 2. Let's paste it in the CPU later. Okay. And let's compile. Let's see if the hexes actually align with our code. Okay, let's go. All right, here we go. Let's start looking from here. Let's see. E3A0100. Okay, great. Okay, correct as well. Here also. Okay, correct, 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 correct. Branching is also correct. Here as well. And let's see, maybe the stack pointer is wrong. Stack pointer function. Nope, it's correct, correct, correct. So all of them basically match. So that's a good sign. That means we have decoded everything correctly. Now let's take a look at the code though. So what is wrong here? Okay, so what do we have here? We have a few move instructions. We copied the value of 0 to R1, value of 10 to R2, value of 0 to R3, and the value of 5 to R4. So we have here a basic loop. So we have sub s, which is going to update the NZSP flags, and we're going to uh, do some subtracting here. We do some addition, conditional addition here as well, and we have the branch. We have the branch. This goes back to loop. Okay, so this is a quite basic branch, so nothing wrong here. Have a function branch here. Okay. Okay, so this is quite normal. So we don't observe an issue here yet. So let's keep going. So uh, we have a link register branch of function to the func label, which is the function label, which is normal. Now everything here is fine until we reach the function label. Why? So here we have a pretty basic store register function here, which stores the link register address to the stack pointer, and that's fine. But as we move on down to the code, we have a few basic instructions here. We have some adds, we have some moves, we have some subs. We have this function. We have this instruction here, bfunc. So what this does is basically creates an infinite loop within our function label. Now, in normal assembly code, this, although it creates an infinite loop, it doesn't actually crash the program. So why in this case do we face a crash? The reason is quite simple. We're using a stack in this code, and the stack does not have a lot of memory, and the stack does not have a lot of memory to use. So basically, as we iterate again and again repeatedly, it cannot go on until infinity. What's going to happen is we're going to is that this code is going to lead to a stack overflow, which is going to terminate the code overall, which is going to terminate the code completely, and it's going to crash. So although in a normal environment, an infinite loop would not lead to a termination or a crash, because we're using the stack and it leads to stack overflow, this code particularly crashes. Okay, so now we're able to understand how to decode hexadecimals into machine code and into actual assembly instructions. And we're also able to identify the relationship between branching and the stack and how infinite loops in a stack can lead to crashes. Thank you very much for watching and see you next time. Bye.